Assalamu alaikum and good evening, everybody, and welcome to the BEAWorld webinar session number 14. I am Numaira Iram, honored to moderate today's session. I'll start by sincerely thanking the organizer, presenter, session chair, and the participants for making this webinar successful. Today's topic of discussion is quantum machine learning, foundations, research, and future directions, in collaboration with engineers and architects Bangladesh, EAB, Abu Dhabi. Special thanks to BE World's collaborating partners, VPDL, Dado, Dell, and Facts Intact. The discussion will last for 30 minutes, and we will have a question and answer session afterwards for 20 minutes. Let me introduce our speaker, Nuzhat Mahdiyat, a computer engineering student at Khalifa University recognized on the President's List. She recently completed a competitive international quantum research program with 14% acceptance rate, where she was mentored by professionals and researchers from the top universities around the world. She has previously interned at multiple companies, including BUET and Dubizzle, a unicorn company in the UAE, and is currently completing a machine learning internship. Her background in competitive robotics, including leading her team to the national finals of the YAS 4x4 Technology Challenge, was translated into her current role as a sub-team lead for the Khalifa University Formula Student Team. She has also built a Mars rover at the Hamdan Foundation Fabrication Lab and completed a research program at Heriot-Watt University on AI. Her recent hackathon wins include the World Future Energy Summit Hackathon and the Pitch to Impact Hackathon at Dubai Chambers, and a finalist in the US Artificial Intelligence Institute Hackathon. Now I will introduce our session chair of today. Dr. M. Mehedy Masud, professor at College of IT and UAE University, and a former assistant professor at CSC BUET. I am confident that today's webinar session will be both enjoyable and incredibly informative for career development. I now request Ms. Nuzhat Mahdiyat to take the floor and begin the presentation.
Thank you, Numaira. Good evening, everyone. Today, I'm going to introduce you to quantum machine learning, starting from how it works, the current challenges, all the way to a research project which I worked on, which was using quantum methods to help detect exoplanets. So let's start with a simple question. Why does quantum computing matter at all? So for decades, computers have gotten faster because engineers could fit more and more transistors onto a chip. And Moore's law states that the number of transistors on a chip roughly doubles every 2 years. But recently, it's been slowing down. The reason for this is that transistors are now so small, around 20 nanometers, that's smaller than a virus, and this causes electrons to start doing something strange called quantum tunneling. So instead of behaving like a predictable flow of electricity, they randomly jump through barriers which they shouldn't be able to cross. And this causes errors instead of speed gains in computing. So researchers took this question that what if instead of fighting these strange quantum effects, what if we used them for a purpose? You may already know what a classical bit is and how it works. It's strictly 0 or 1, and there's nothing in between. However, a qubit breaks that rule. Instead of being locked into one definitive state, a qubit can exist in a superposition, which is a combination of both 0 and 1 at once. So we can write this mathematically. There's no need to memorize this, but I will just explain what it means. So 0 and 1 are just our two basic probabilities, and alpha and beta are complex numbers that tell us how much each possibility is mixed into the qubit's current state. So if alpha is large and beta is small, then the qubit is mostly leaning towards 0. And if they're roughly equal, that means it's a more balanced mix of both. We can actually visualize this using something called the Bloch sphere, as you can see. So think of it like a globe. So the North Pole represents a definitive 0, and the South Pole represents a definite 1. And every other place on the surface of that sphere represents some superposition, basically a blend of the both states. And the arrow that you see pointing outwards shows you exactly where the specific qubit state is at currently. So now two qubits can also become entangled, as you can see at the top. So when qubits are entangled, they become linked in a way which can't be explained by classical methods. Like there is no classical equivalent. So when you measure one of them, it tells you something about the other qubit instantly, no matter the distance between them. And superposition, shown below that, is really what makes a qubit different from a bit in the first place, because a qubit can exist in that in between state until the moment that you measure it. And at that point, it is forced to collapse into a definite 0 or 1. So before going further into the quantum side, we need to make sure that we understand classical machine learning. Since everything that we do about quantum, it still needs this foundation. So in the simplest way, there are actually four steps. So first you have data input. You gather your raw data, whether that's graphs, tables, or images, etc. And second, you have feature extraction. And this is where you pull out the parts of the data that is actually important and that actually matters for your task. And third is model training. This is, in fact, the most crucial part because here is where the algorithm learns the pattern from the data. And fourth is prediction and evaluation. So you test how well your model actually performed. So learning means that you're finding structures in the data so that you can make predictions on the examples which you haven't seen before. So this process is the base for machine learning because everything that we do, even in the quantum world, is aiming for this exact same goal, which is of training and prediction. However, it's just using a different process underneath. So that question leads us to quantum machine learning or QML. So, to understand where QML actually lies, you need to ask yourself some questions. So, is your data classical or quantum? And is your computer classical or quantum? And that gives us four boxes. Classical data on a classical computer, that's just the standard machine learning which we all people already use. And quantum data measured with classical tools, and that's called quantum measurement. And fully quantum computers processing fully quantum data, that is the future state. It is still mostly theoretical today. But in the bottom left, you can see that we're using quantum computers to find patterns in classical data. And this is the current frontier. And this is where almost all of the current QML research is happening today. So I mentioned earlier how quantum tunneling can cause electrons to behave differently inside classical transistors, which basically becomes a source of noise, and that can limit how small the chips can get. So QML approaches this problem completely differently. So instead of only trying to eliminate the quantum effects, it asks that whether some of these effects, especially superposition and entanglement, can actually be utilized as a resource rather than being treated as noise so that engineers can just work around that. So QML sits at the intersection of quantum computing and machine learning, as well as exploring the best ways to apply these quantum methods. So, to be clear, the focus of this field as of now isn't replacing classical machine learning everywhere. It is still an open research question that are there specific tasks which can give us a real advantage? And the goal is to explore that whether this large space of possibilities can help us speed up certain learning tasks. So let's talk about how a model actually learns, because this is how both quantum and classical machine learning would follow. So I have a graph here. So I want you to imagine that you're standing somewhere on this pink hill and you're trying to find the lowest point, which is the valley. So this landscape represents something called the loss function. And the loss function is a score of how wrong your model currently is. So the higher up you are on the hill, it means your model is very wrong. And when you reach the valley, that is the closest it is to being correct. Now, training a model basically means that you're walking downhill step by step until you reach this minimum point. And this process is called gradient descent. And each step, as you can see here, theta 0, theta 1, theta 2, the model checks which direction is downhill from where it currently stands, and then it will take smaller steps in that way. And this formula captures that idea mathematically. So your new parameters equal your old parameters minus a small adjustment in the downhill direction. So we have alpha here, and alpha is called the learning rate, and it controls how big each step is and how quickly your machine is learning. And getting that learning rate is actually very important. So as you can see in the small graphs, if your alpha is small, so you will get this smooth curve. It's a gradual curve, and you reliably reach to the bottom and you reach slowly. However, if your alpha is very large, you get this wavy pattern. So what happens is basically you start here and you overshoot this valley, and that is what results in this graph. So you have almost like a sinusoidal curve. And as you can see here, you have a bar chart, and it shows what successful training actually looks like in practice. So the cost is steadily decreasing with each iteration. And if you remember the cost function, that is how wrong the model currently is. So given those parameters, how wrong the model currently is given those parameters, and that is exactly what you want to see to know if your model is learning correctly. So now I'll explain a word that we're going to use a lot, which is dimensions. So I'll explain it from a data point of view. So think about a spreadsheet, and it has people's biodata. So if your data set only tracks one thing about each person, let's say their age, and that gives you one dimension. So you can describe everyone with a single number. Now, if you add a second column, let's say their height, now each person needs two numbers to describe them. So that is two dimension. And if you add income of the person, that's three. So every column that you add gives your data set another dimension. And it's basically another independent piece of information which you need so that you can fully describe one person. So another thing is that if we're talking about real data sets, they will obviously have more than three columns. They may have 10, 50, 100 features. So we can't visually picture a 100-dimensional space, but mathematically it will behave exactly the same way. It's just a data point that would need 100 numbers to represent it instead of two or three. So now I will discuss about the quantum feature maps. So as you can see here, you have a circuit that is u of x. And what it does is that this step is taking your data, your columns, your features, and it is encoding them into a quantum state. And that space that data gets mapped into is called the quantum feature space. And it also has dimensions just like your data set did, but the difference is how fast this space is growing. So if you look at this table here of exponential growth, with 2 qubits, you get 4 dimensions. With 3 qubits, you get 8 dimensions. With 4 qubits, you get 16 dimensions. So as you can see here, you're not just adding the qubits, but it is doubling every time. The dimension is doubling every time you add 1 qubit, and that is like a completely different growth pattern compared to a classical data set, where you add one feature and that just adds one more dimension once at a time. So every added qubit is not just going to add a little bit of room, but it is going to double this entire space, and it's going to compound extremely fast. So by the time you reach 275 qubits, you will have more possible states in that space than there are atoms in the observable universe, and that is a mathematical fact. So this is like a direct consequence when you keep doubling 2, 4, 8, 16, 275 times. That is the result. So having a bigger space of possibility doesn't automatically mean better machine learning algorithms. So whether this enormous dimensional space actually helps us learn patterns more effectively, that is still an open research question. And we'll come back to that as to why that is not guaranteed. So once our data is encoded into this quantum computer, we need something trainable. So something with adjustable knobs. So we know in a um, classical neural network we have weights, and that is also an adjustable parameter. And similarly here, we have something called the ansatz. And the ansatz is also known as a parametrized quantum circuit. So in this diagram, our encoded data, which was the feature map that we saw, it flows into this parametrized variational quantum circuit, which has tunable parameters, which we call theta. And we can measure the output, calculate a cost function, and then you can see shown by the red arrow, we use that optimization step and adjust theta, and we repeat this loop over again. So these parameters, theta is basically the quantum equivalent of the trainable weights that you would see in a classical neural network. So this diagram kind of ties together everything that we covered into one picture. So on the left, you have the classical neural network. It has the input layer, the hidden layers, and an output layer. And in the middle, we have an interface, and this is where the classical information is getting handed off to the quantum circuit. So on the right, we have, sorry, on the right, we have the quantum circuit. We have the Hadamard gates, which is marked by H, and the Hadamard gates create superposition, and the entangling gates create a correlation between the qubits. And finally, we measure the result. And below you can see a summary of this hybrid loop. The reason we say it's a hybrid loop is because it's using both classical and quantum methods. So the quantum computer produces a result, the classical computer uses it to update the parameters, and this cycle repeats. And this is how a hybrid quantum classical model is built. So by now you've seen this same core building blocks repeat. You encode data, you run it through a trainable circuit, you measure, and then you optimize. So this loop is the backbone of every single QML model that you would encounter today. So if I were to talk from like a systems point of view, this is another way to view it. So on one side, we have a quantum processor, and on the other, we have a classical computer. So the quantum processor evaluates the circuit and it calculates a cost function value. As we mentioned, that is how wrong the model currently is. And that result gets sent to the classical computer, which runs an optimization algorithm. It will compute the gradients and it will update the parameters. And those updated parameters are sent back to the quantum processor, and this loop continues. So it's like a partnership between the two. So as of now, we don't really have a fully end-to-end quantum training pipeline. That is something we can see maybe in the future, but according to research, that is something that's not possible for a really long time. So let's talk about one really well-studied specific technique, which is called quantum kernels. And a quantum kernel is a function that measures the similarity between two data points. So the core idea, as you can see in this diagram, is that data is tangled up and it's inseparable in a low dimensional space. And however, this can become separable once you map it to a higher dimensional space. So on the top row, you can see how a quantum encoding circuit maps that raw data into a Hilbert space, which is basically a high dimensional space. And in the bottom row, you can see the classical equivalent. So where you're mapping data using a classical function phi. So both approaches ultimately compute something called a kernel. And a kernel is the similarity score between data points. And this feeds into the classical classification algorithm. So in this case, there is a support vector machine, which is also a classical classification algorithm, and that is used for the final decision. Of course, there's a lot of linear algebra math behind this, but that would be another deeper topic. And another point here is that there is a lot of hype behind QML. So as we know, classical kernels, like the kernel that is used in the SVM, can already do this mapping pretty well, and they have been doing that for decades. So what is potentially different about the quantum feature maps is how this similarity is getting computed and how it is offering an alternate approach. So this isn't like an exclusive access to separability itself. Separability of data was already achievable with with classical methods as well. But however, quantum kernels, it's still a promising research direction. So let's discuss where QML currently struggles. And these are real active problems. They're not just minor inconveniences that you can just engineer around, like with a bit more effort, but these are like actual problems that researchers have been actively trying to solve for years. And in some cases, there's still not a complete solution to all of these problems. So first, barren plateaus. So if you remember the lost landscape over here, so as we scale up and as we scale up and we have circuits with more qubits, the loss landscape, remember the loss functions that we see here, it can become exponentially flat, which means the gradients vanish and the training will stop entirely, that this gradient will not even exist. And that is the barren plateau problem. And second is noise and decoherence. So today's quantum hardware is it's quite imperfect. We are currently in what is called the NISQ era, and the NISQ era is basically noisy intermediate scale quantum. So there's environmental interference, there's heat, electromagnetic interference, and even tiny vibrations. And this causes qubits to lose their quantum state over time through a process called decoherence. So the deeper that your circuit is, the more operations it's going to run, and the more time passes, and it just gives you more opportunities for errors to enter and accumulate. So this is like a real ceiling on how large or complex of a circuit that we can reliably run on today. Third is the data loading bottleneck. So if you remember the feature encoding step from earlier, it turns out that that step can be computationally very expensive. And this is an important point because even if your quantum algorithm is fast, once the data is loaded, and if loading that data takes just as long or even longer than the entire classical alternative would have taken, you've basically gained nothing. So sometimes this loading cost is expensive enough to completely cancel out any speed up that this algorithm would have promised you on paper. And this is often called the input problem. And it is one of the most common reasons, even though like an algorithm is mathematically very beautiful, very promising, it doesn't really translate into like practical advantage. And for dequantization. So this last one is less about the hardware limitation, but several early high-profile claims that these that this exponential quantum speedup is going to completely give us a new advantage and replace classical machine learning. It was actually matched by the newly discovered classical algorithms. So, in other words, once the researchers looked harder, they found that the classical computers actually caught up. So, some historic QML advantage claims were simply didn't hold up after the researchers did a closer scrutiny and they found that there were better classical methods existing. And I think this is one of the most important lessons in the entire field because it's a healthy reminder to question the bold claims, because including some of the most exciting ones that you've heard today. So QML is a promising, it's an active area of research, but it's not a guarantee that quantum will replace classical machine learning entirely. So, being honest about that rather than overselling it is what makes this a credible field still, rather than just creating hype. So, given all of that, Where is QML actually being used or explored today? In drug discovery, simulating molecular interactions is extremely costly if you are trying to use classical methods. So, quantum methods can help with that, and it can model those interactions more naturally and more efficiently. In biotechnology, complex biological systems have many interdependent variables that quantum models can capture more effectively. In finance, portfolio optimization, it means you're selecting the best combination of assets from thousands of possibilities, which is an exponential problem that quantum algorithms are actually being tested against. And similarly, you can use it for risk assessment and fraud detection, where you can spot rare and subtle patterns in huge transactional datasets. And finally, scientific data classification. When you have high dimensional, noisy datasets like telescope signals, these problems are much naturally suited to the quantum feature spaces. And the last one is exactly where I did my own research on, and I will discuss a bit about that. So, this project was a part of a research program that I did called Beyond Quantum, and I did it over 12 weeks. So, after being trained on various skills and topics, including how to approach topics from a researcher's point of view, which is completely different from just selecting a topic and doing a Google search. We learned how to do research stand ups, which is basically where you verbally present your research to an audience, you get feedback, you answer questions, and then you improve your own research. So all of this greatly improved my confidence in talking about technical topics and condensing my research into a speech. So apart from this, we attended lectures in quantum mechanics, the math behind quantum, and I was simultaneously doing differential equations and linear algebra course at university. So this was a really good bridge to connect the ideas that I was getting from my classes as well as the program. And this program really challenged me because the discussions and the assignments weren't simple problems to solve. It really challenged the way that I thought about scientific and mathematical concepts. But staying consistent over a long period really helped me advance to the research stage. So I had to solidify my understanding of classical machine learning and QML before even taking the course, and then using the new coding frameworks and also applying QML. So all of this knowledge was pretty fresh in my head, and I had to quickly apply them. So in the research stage, my teammate from Poland and I chose QML domain, and what we had to do was basically build on a previous research project. So analyze their methodology and decide what can we do differently or what hypothesis can we test. So the previous project was comparing classical and quantum methods for exoplanet detection, but it was using quantum as the entire classifier. It was a full VQC pipeline. So we decided that what if we change the stream of how data flows, basically creating a different pipeline. So we used a hybrid approach. And this project asks a specific question, that how does a hybrid quantum classical feature extraction pipeline compare to purely classical models when classifying Kepler exoplanet candidates? That was a research question. So, some quick context for the dataset that we used. So, NASA's Kepler mission basically identified thousands of exoplanet candidates by its telescope, but many of these turn out to be false positives, and this can be caused by things like stellar noise or binary star systems. So, a binary star system is when two stars are orbiting each other, and from far away it can look like a planet signal, but it's actually not. It's actually just two stars. Our data came from the Kepler object of interest table, and each sample is labeled as either a confirmed exoplanet or a false positive. So we built two classical baseline models. First, logistic regression, which is a simple classifier, and second, a classical neural network. And it was a fully connected network that could learn nonlinear relationships, and we compared both of these to our hybrid quantum classical pipeline. So as you can see here, we used angle encoding through the U gates to get our data into the quantum circuit, and that same It's the same encoding concept which I spoke about. We also used the circular C-naught entanglement to capture non-linear relationships between features, and we used a 5-qubit circuit, which gave us 32-dimensional quantum feature space, which is 2 to the power of 5. And we compared that to the classical, a standard preprocessing technique, and this only compresses data linearly, and this classical technique can also discard any useful information in the process. In our hybrid architecture, the classical preprocessing handles the scaling, and the quantum circuit encodes and transforms the features, and finally those extracted quantum features get passed into the classical neural network for the actual classification decision. So to be precise, the quantum component performs the feature mapping while the classical model performs the learning and classification. Now, over here we have the results. So all three models, logistic regression, the classical neural network, and our hybrid model, actually achieved a very high recall, overall 0.99. And a higher recall means that all three of these models reliably caught a true exoplanet signals. So they rarely missed a real planet. So the classical approaches actually outperformed our hybrid models on two metrics, which was the OROC and precision. However, the quantum model still remained genuinely competitive. It was very close on multiple measures. It was not far off at all. So what does this mean? Our results suggest that the quantum feature extraction shows a real promise for astronomical classification tasks, that is the data that we used, but it didn't outright beat the classical methods in this particular study. But what we can take away is that this is still a legitimate, useful research finding, because not every experiment needs to follow the exact hypothesis to be valuable. And the honest, useful result that we got is that this method is competitive and it is worth to continue exploring. That's all from my side. Thank you very much for your attention, and I'm open to any questions.
Thank you, Ms. Nuzhat, for that excellent presentation. Your presentation is truly inspirational and encouraging. Now I will invite our chief guest, Mr. M. Mehedy Masud, to share insights in today's session.
Thank you. First of all, I would like to thank organizers. Uh, can you hear me well?
We can hear you.
Thank you. So, uh, Engineer Reza Bhai and the organizers, thanks for organizing this kind of inspiring sessions. And we are listening to, we can say, our future leaders and researchers in the cutting edge topics. Thanks, Nuzhat, for your nice presentation. We learned a lot from this. So I will not just take much time. I requested Reza Bhai to give me floor beforehand because I have to leave early. So that's why the question answer session will be right after this. I just, since we are in the mainly the audience, I believe mostly from engineering background, we have civil structural engineers and electrical engineers. So I would like to highlight just one or two use cases where quantum machine learning could be very useful. So one of them is in terms of civil engineering, the application for smart material and structural health. For example, prediction of micro crack propagation and stress distribution in concrete and advanced composite materials. So this is a big problem, especially for structural engineers. And classical machine learning methods for this kind of prediction of microcrack is very difficult because it needs to be done in the molecular level. However, because of these quantum kernel methods, they use very efficient parallel processing. This problem can be solved much efficiently with the quantum machine learning. Secondly, for electrical engineering, the application for grid optimization and renewable integration, real-time load forecasting, and optimal power flow. So this is another problem with the recent smart grids and these things. And classical machine learning also uh, is very challenging because it is a very big uh, optimization problem. It's called NP-hard problem. However, using the model's quantum approximation optimization algorithm, they call it QAOA, it can handle massive topological grid data sets, and therefore this problem can be solved much efficiently. Now, moving on to the final part, this, as Nuzhat said, this might be in fact, quantum, when we heard about quantum supremacy, this can look like a very ambitious, but this is also kind of a hype because if you're talking about a fully fault-tolerant quantum supremacy, we are actually decades away because there is lots of noise and other things. And also the other problem that Nuzhat already mentioned, this the data loading problem. The problem is in the classical computers, the data storage and data loading, it is totally different in the quantum machine learning. The interfacing is extremely difficult, and therefore this data loading can take all the bottleneck. So there are active research on this, and hopefully things will get better soon. And still, uh, quantum machine learning may not be the best for everything. For example, when you are talking about standard image or text processing, still the classical deep learning wins very easily. However, quantum neural networks can be optimized to have much less parameters, and it can solve the uh, nowadays we have the big problem with the energy crisis for AI compute and these things. So this problem can be solved with this paradigm shift and pivoting to the quantum machine learning. So that's all I wanted to say. And again, thanks everyone for listening, and thanks Nuzhat again for your excellent presentation.
Thank you, Dr. Mehedy Masud, for your engaging speech. We will now open the floor for questions. If anyone has a question for our speaker, please raise your hand, or you may post your question in the chat box. I see that Mr. Esam Rahman has raised his hand. You may ask your question.
Thank you, Nuzhat, for a wide and in-depth presentation. Very nice. I have a question. Is there any drawback or error of misleading the real fact by approaching quantum machine learning?
I'm sorry, could you please repeat the question?
Is there any drawback or error of misleading the real fact by processing quantum machine learning?
Are you talking about how if our data set can become, if there's going to be any missing data in our data set?
No. By quantum machine learning, if we process something, is there any drawback, disadvantage, or error of misleading the real fact Do you think it's
I think probably I understood the question, if I understood correctly, uh, Athorwai. You are asking if whether there is a possibility that quantum machine learning output can be wrong and it can be misleading, right?
yes, yes.
All right.
Okay, so I'm not exactly sure about this part yet. There are disadvantages, like I mentioned, the different challenges in quantum machine learning, but obviously, like I mentioned in my research project, I'll just take it out. We actually measured like multiple components, like the precision, the accuracy, even OROC, which is like this curve which you can determine how correct your model is. So BS has different metrics, and obviously no model is going to be 100% correct. Even classical models, there is like a degree of uncertainty, and the same applies to quantum methods as well. I hope that answers your question.
I see that Miss Rapunzel has raised her hand. You may ask your question.
Okay, can anyone hear me? Like,
We can
Yes,
hear
you're
you.
clear.
yeah, the session was amazing, and I have this one question, which is, what is the advantage of using quantum kernels over classical kernels?
Okay, so when we're talking about quantum kernels, it can help us in a few ways. So, a kernel is basically measuring the similarity between two data points. Now, if we have two dimensions, it means that there is a lot of data that is clustered together, and we need to separate this data and to see the differences between them. For example, if you have a red car and a blue car, and you want the algorithm to differentiate between the two, where do you draw the line that this is a red car and this is a blue car? That is what I would say we're using quantum kernels for. And when we have this higher dimensional space, as you can see, the data points are separating. You can see where each data point lies. Imagine if you had all of this data clustered into a flat piece of paper. It would be much harder to do that. However, when you have a kernel, it can map this into a much higher dimensional space.
Thank you.
You're welcome.
I see that Mr. Raghib has raised his hand. You may ask your question.
Yeah. So you mentioned that classical machine learning is already really good at handling classical data, and QML still faces challenges like noise and the encoding stuff, the delays. So what keeps researchers still optimistic about QML? Could it like eventually do things that classical machine learning just can't in the future?
Yes, that is still an open research question. The reason that researchers are going forward is because um, that they want to see if it can somehow be a close competitor, even though if it's not going to surpass classical methods, if it can provide us an advantage in certain tasks. It's not that we want to use um, quantum methods to do every single possible task. Like Dr. Mehedy mentioned that if it when it comes to like text and images, it is better to use classical methods. But for example, here, I can talk about one problem that we faced when we were doing this project is that instead of using the Kepler objects of interest table, there are actually there are way more different types of data. So there was these diagrams, these graphs, which had like informations about different planets, and we were trying to figure out how we can use this. So should we try reservoir computing? We were testing out so many different quantum computing techniques. And then eventually we realized that we are limited because what we're using was Qiskit, and Qiskit is only a simulation of the real quantum computer. However, when we try to use this in a real quantum hardware, obviously we will be getting different results. So as of now, running it on a real quantum hardware, if we use IBM's quantum cloud platform, it's obviously very expensive, and there's limited opportunity to do so. I think there's only 10 minutes of computational time. So yeah, the researchers are hopeful because it's not just using solely quantum methods, but they're trying to figure out, can we use the hybrid methods? Can we combine classical and quantum methods? So it's just researchers are curious, like how everyone is, how students are curious. It's the same motivation that's taking them forward.
Okay, thank you.
Mr. Asimatur Rahman, you may ask a question.
Yes. What are the area or sector we can use quantum machine learning in Bangladesh now?
How we can use quantum machine learning in Bangladesh?
In Bangladesh, in which area or sector?
Okay.
Area.
In area, okay, so there are different applications and sectors that we can use it. So when it comes to pharmaceuticals, drug discovery, um, we can use quantum machine learning in computational biology, anything that has to do with if we're doing computational chemistry, computational biology, um, and we want to simulate these molecular interactions, we can use this. We can use quantum machine learning for that because it is very costly to do that in a classical way. And also, I know Bangladesh has like a space center, and obviously there is a lot of data incoming from satellites, from any rovers that are in orbit. So that scientific data from space can also be used. And I think another area of usage is, it's a bit unrelated to this, but it can be through the usage of satellite data and digital twins, and that can help us basically simulate different like climate disasters so that the country can be better prepared. That is a topic which I tackled in a previous research project, but then I realized that some quantum methods can also be applied to that. And obviously, we have finance. So, in the banking sector of Bangladesh, in accounting, it can be used. So, yeah, overall, scientific data is definitely one of the strongest parts. I could even say agricultural data, but I'm not 100% sure about that. But any data that is very high dimensional can, it is very much suited to use these quantum methods.
Thank you so much.
Does anyone else have any questions? All right, with that, we end our question and answer session. Thank you all for your active engagement. Now I will invite Dr. Sajid Hossain to share a few words on today's session.
Thank you very much. First of all, we are very much thankful, and our felicitations again for the organizer BEAWorld, and particularly coming down to today's presentation. This is a very high tech area, although personally I'm not any expert on this, but at least the basic things, it is understood that besides the not, 0 and 1 or binary digits, the qubits, and again the quantum computing is with the being blended with the machine learning, and purpose of all these things is to assist or enhance AI models in its speed and capacity. Therefore, this is undoubtedly a very complex and high-tech area. What has been very successfully presented by today's keynote speaker, Ms. Nuzhat. I cannot see the full name anyway. You have really presented in your capacity. I'm very sure that among the audience, those who are present, in general and in particular, more or less everyone have been blessed with new things, interesting points to be noted, and definitely those who are related by work, by research, by academic works anyway, they will be no doubt that they will be benefited. They are benefited already. And your presentation style and other things, everything was very acceptable, welcoming, and therefore I'm pretty sure and confident that the ongoing activities by the BEAWorld is getting much benefited and mature by presentations like this one, and particularly today. So Ms. Nuzhat, congratulations to your presentation today, presenting a very complex one in a very understandable, easy manner. The anchor of today, Ms. Numaira in Iran. Thank you very much. And I'm in what capacity, I don't know, but definitely from since beginning, I'm with the as an well-wisher of BEAWorld. I'm here, and today, from my side, we can conclude with a full satisfaction. Thank you very much.
Thank you, Dr. Sajid Hussain, for your kind words. With that, we conclude today's session. Thank you all for joining us, and we look forward to seeing you at our next webinar. Have a wonderful evening.